Hi, and welcome to this refresher lecture. This lecture is not intended to be an introduction to inferential statistics. The reason for that is that each of you should have already completed a course in inferential statistics, my course, ENVS 1003. And you will remember that that course introduced you to ideas around types of data, data handling, and also some basic inferential testing. Now, the reason ENVS 1003 is a mandatory component or a prerequisite for this course is that we're going to get started straight away into new statistical content. Some of it will be familiar because we will need to refresh your understanding. Some of it will be completely new. We don't have time, because it's a short course, to cover all of that inferential content that we covered in ENVS 1003, nor should we, because you're already familiar with that to some extent. But it's probably appropriate for me to cover some of that content very quickly in a refresher lecture, so that when our lectures for 2002 start in the first day, you're already warmed up, you're ready to go, and you have refamiliarised yourself with that content from 1003. So this lecture here is intended to do that. Now bear in mind that it's not just this lecture that you should complete before the course. There is a practical activity associated with this lecture content that you should step through before ENVS 2002 commences. The reason for that, well, there are a few. First, the practical activity uses JMP. If you've recently completed ENVS 1003, you'll still have a live version of JMP on your machine. If you completed JMP last year or year before, you won't have a version of JMP on your own machine that you can use within the course, and you'll need to install JMP again. Now to do that, you just go to the Wattle page for this course, and you'll see that on the front page where it says install, JMP is right next to it. Now instead of downloading a version of JMP that you'll have access to for the next year, it's easier and it's quicker for us to make use of JMP's free download or free trial version of JMP. So for this course, we'll be using the JMP free download to run all of our analyses. It's a full version of JMP. It just has a short license, a 30-day license. And of course, that will see us out for the entire course and all of the associated assessment. The other reason, of course, for doing this is because the analyses will remind you of the concepts that t-testing, ANOVA are based upon. And they are key concepts as we move forward into the rest of the course. So make sure you complete both this theoretical content as well as the practical content before the first day of the course. That is before November 20. Not doing so will really impair your ability to engage with the analyses and the content on that first day and from there on. So let's get started. Behind me are two graphs. Now these two graphs share a great deal in common. There are some obvious differences. Now, what are these data? Well, really, in a sense, it doesn't really matter what these data are, but let's just have a look at them. We can see that notionally there are two sites, and on the x-axis, we have separated the data into two levels. Some factor on the x-axis, whatever it is, it separates our data into factor A or level A and B in the factor. It does the same thing in the other graph. On the y-axis here we have some form of a response, some measurement, some quantitative continuous variable that we have measured of some individuals, whoever they are. So these graphs share a great deal in common. The similarities are things like what we find on the x-axis, a nominal or an ordinal variable that we can break into categories. On the y-axis, we have a continuous variable. We've measured something using a quantitative technique. So we have two levels. We have an ordinal or nominal variable, and we have a continuous variable on the right-hand side. And you can see those key elements there, those first two elements shown in these three dot points. The third point, though, we can see that the data within each of the two levels, A and B, are relatively evenly distributed with a slight concentration at the middle. And so the distributions are largely unskewed or non-skewed. You can see that too here for level A in site 2, slightly less so down here in level B, but you know, it's largely unskewed. All right, so there's consistency there between the two graphs. Now, let me just back up a second here. There are other ways, other than simply presenting our raw data like this, there are other ways of presenting data, and you'd be familiar with those. In ENVS 1003, for example, we introduced box and whisker plots, and you're probably familiar with them already. You were probably familiar with them before you entered into a course like ENVS 1003. The box and whisker plot. Something you should be familiar with as you move through your career, through your degree, is exactly what a box and whisker plot represents. Remember, the box here in the middle represents the quartiles, the 25th, 50th and the 75th quartiles of the data. So 25% of the data sit between this lower edge of the box and the end of the whisker here. Then the next 25, the next 25. So the middle 50% of the data sit in there. And the whiskers represent either the full spread of the data, or if it's a very, very dispersed data set, represents 1.5 times this interquartile range. Now, our data here are not very widely distributed, so you can see that the whiskers are quite narrow. So we have data that is relatively unskewed, and we don't have a very wide spread. So we can see that pretty quickly from a box and whisker plot. Now, why do we use them? Well, because they give us that information very quickly. At this point, before we get into quantitative analysis, it's worth remembering that the first thing you should always be doing with data is looking at it and using quick observational techniques, qualitative techniques to assessing your data. And this is a really great one. It's a semi-quantitative approach. It summarises our data into a nice, neat graphical form that we can interpret very quickly. Now, there are other ways of representing our data, and one that you'd be familiar with from ENVS 1003 is the confidence interval. And here I've put some confidence intervals over the top of the box and whisker plot. Now, remember that confidence intervals represent a defined level of likelihood of including the population mean from which we have drawn a sample. So here we have inserted this dark point in the middle, which represents the mean. And you can see the mean represented up here for those two levels. And the same for the second site. So you have two means separated by level A and B. You can see that represented in both of the tables. Also associated with those means are these error bars. And in this case, these error bars represent, well, what do they represent? Well, in this case, they represent a standard deviation. Now, that standard deviation you can see represented up here. All right, so we have a standard deviation represented on each graph, shown as an error bar around the mean. Now, of course, the standard deviation is not our confidence interval. Our confidence interval, remember, is calculated using a few things. First, you can see down the bottom here is the equation for our confidence. This little x with the bar on top, remember, that is our mean, our sample mean. So x bar sits either here for level A or here for level B, and then likewise for the second site. So we have our mean, and then we have an interval around it. So we calculate an interval above, a limit above, and then a limit below. So we have this plus or minus approach. Now we have two components to that calculation, a t and this SE term over here. The SE term, remember, that is our standard error. We calculate that as the standard deviation of our data set, so 7.61 in this case, divided by the square root of n. So the standard error in the case of level A on site 1 is 7.6 divided by the square root. T, however, comes from, as you might remember, from the student's T table, and it represents the number of standard errors that are required to include a defined likelihood of capturing the population mean. Sort of sounds like I'm talking in circles there, but I'll show you a reference that'll be useful for you to have a look at if your memory of the confidence interval isn't as good as it might be. But first, let's have a look at the T. Remember that the T distribution draws from what we refer to as the Gaussian or the Z distribution, the likelihood of capturing a population mean based upon a very simple concept, the concept of the central limits theorem. The central limits theorem simply states that you are more likely to capture a population mean or an individual sample mean close to the population mean than far away. Or rather, if you resample over and over and over and over again, gradually your mean of the means that you generate from all of your resampling will fall very close to the population mean, more likely than far away. Now, from a practical point of view, what that means is if we sample, with one important caveat, if we sample, we are more likely to obtain a value close to the population mean than far away. Remember what that caveat was? That caveat was that we draw our samples using a random sampling approach. Now, in many instances, we use systematic sampling approaches, but we rely on the attributes of the data set or the sample population itself to introduce a randomized element into our data set, even when we use a systematic sampling approach. All right, so we have a normal distribution. Now, if we have different sample sizes, that changes the shape of the distribution a little bit. So if we have a small number of samples as opposed to a large number, you can see that for a small number of samples, the distribution is quite widely spread relative to a distribution for a large number of samples. And that explicitly reflects the uncertainty that comes with having a small number of samples relative to a larger sample. So the size of our sample affects our certainty, just like everyday life. The less you know, the less information you've gathered about the world around you, the less you can infer with confidence. So it works exactly the same way. This is a formalized way of representing that in quantitative data. Now, our T values, or the T's that we use in calculating a confidence interval, are not just determined by the number of observations we have. They are also determined by the level of confidence we want to have when we estimate our confidence interval when we're trying to estimate our population mean. And you can see that represented over here in this graph from this excellent paper that comes from Nature Methods. And if you are at all uncertain about some of this content, this is the paper to have a look at online. Significance, p-values and t-tests in Nature Methods. It's free to access for everyone and it covers the content that you need to understand pretty well. And these two graphs are drawn from that paper. Now to come back to this panel over here, what we can see here is that not only does the number of samples impact upon our derived t-values that then represent a section of this distribution, not only do the number of samples we measure affect that, but also the level of confidence we want to have. How is that shown here? Well, it's shown here in what is referred to as the p-value. When we calculate confidence intervals, we refer to that as the significance, or often alpha. Now let's just go back one slide and see that. You can see that down here. The t is defined by, yes, number of observations -1, our degrees of freedom, but also this alpha term, the significance. How do we know what the significance is? Well, ordinarily in most research fields, we apply a confidence interval of 95%. Significance in that instance is represented as 1 minus 0.95, the proportionate likelihood. And that would give us a p-value or a significance of 0.05, and then we derive our t-value associated with that significance or p-value. Now we can change that. If we want to be more certain, we can include a stricter confidence level. We want to be 99% sure, for example. We have a p-value of 0.01. Where maybe we're willing to accept 90% likelihood. Well, then we have a p-value of 0.1. But more generally, our p-value sits here at 0.05. So we need a mean, we need a t that's given to us by our alpha value or our significance here on the y-axis, as well as the number of observations represented in the individual curves themselves, and we need our standard error, standard deviation divided by n. Of course, you don't need to do any of these calculations by hand for a couple of reasons. One, students' t-tables always have the same values in them and you can use those. But more realistically, we use statistics packages and they do the calculation for you. It's important, though, it's useful to have an understanding of where these calculations, where these numbers come from, though. Of course, you already know all that because you've done ENVS 1003. All right, so let's come back to these graphs. We have two graphs, largely showing the same kind of stuff. We have a nominal x-axis, we have a continuous y-axis, we have pretty much non-skewed distributions. And we can see that because, well, the means represented by our little circles here in the middle and the medians, the middle line in our box, the means and the medians are more or less the same. There's a little bit of variation over here. You can see the means here is a little bit above the median, same there. But these two, they're pretty much bang on. The means and the medians are pretty similar. What that tells us is that the data are, well, slightly skewed perhaps, but not very seriously skewed. The means and the medians are very similar to each other. All right, so we're starting to see quite a lot looking at our simple box plots. So there are a couple of key points to take away. First of all, we're looking at two plots of data, two plots of continuous data on the y-axis. Both of them have two levels on the x-axis, and both of them include data that appear to be normally distributed. That's important because those three criteria are 3 of the 5 requirements for us to use a t-test or a test of the means using our t-statistics. those t-statistics that we were talking about only a moment ago. So there are 3 here. Apparently there are 5. So what are the other 2 of those 5? But first, let's understand what t-testing actually involves. All right. So this again is drawn from that same paper. Again, go to that paper and familiarise yourself with it. It's not accessible by any means, but it is a useful paper to start refamiliarising yourself with this inferential statistics content without going all the way back to ENVS 1003. All right, so the idea of a hypothesis test that we use to test means. Remember, in ENVS 1003, we started with the idea of testing an observed value relative to say a reference value, or a population value, or some threshold value that we have assumed prior to our study. Right, so we go out, we collect data, and we calculate X, and we're going to compare it to an assumed population value, mu. Now, based upon our data, the number of observations we have, the standard error, and our t-value, we can calculate a curve, a t distribution based upon, again, the number of observations we have. And then, based upon that t distribution, we can say, well, our x value sits, a long way out here. What proportion of the data set, the theoretical means, what proportion of those means is covered by this x here as a threshold value? So if it were close in here, as opposed to sitting out far out here, what is the likelihood of achieving this x value out there? That likelihood is what we refer to as the p-value. And typically, statistical tests use that p-value. The likelihood of achieving this value here by chance. Remember that the p-value represents the likelihood of our data, the likelihood of H0 being true, that is that there is no difference between x and mu. What is the likelihood that those two actually represent the same thing given our data? Well, if it's a very small likelihood, it's unlikely. If it's a large likelihood, it's quite likely. But of course, more and less are quite qualitative terms. We need something a little more solid than that. How do we define what is less likely or more likely? Well, we have that threshold, artificial as it is, we have that threshold of 0.05. Any p-value less than 0.05, we say that we have evidence to reject H0. We think that there might be a difference between mu and x. Or if that p-value is larger than 0.05, we don't have evidence to reject H0. So that's the way that testing operates when we have a single value and we're comparing it to a threshold value. Now remember, as I highlighted earlier, one of the key caveats here is that our samples are drawn at random. And that is our fourth condition associated with testing. We have randomly sampled independent observations. And if you need a reminder of the process here, here is another of those Nature Methods papers that is really worth having a look at. Download it, look at it straight away or look at it later, but honestly, if you're unsure, look at it now. This is a great paper that introduces you to the idea of the central limits theorem and how even a randomly distributed data set can deliver a normally distributed population of means. Okay, so we looked at this first example here, where we compare a single sample to a population mean. We calculate our sample mean, we use the sample data to generate a confidence interval. Okay, so we start with our standard deviation, we calculate here a standard error. You can see the variance of x divided by n, which is the same as the standard deviation on the square root of n. So we start with standard deviation or variance, and then we move to our standard error, and then based upon our standard error and our t-value, we calculate the likelihood that H0 is true. Now that's great if we only have one sample. What if we have two? Well, in those cases, we have two measures of variance. Of course, that gives us two measures of standard error. And then associated with that, we can integrate those two measures of standard error into a single term that represents the difference between our two terms, our two means. So in the top here, we are comparing our mean of x to a threshold value using a single standard error term. The bottom one here, we're comparing our mean of x to our mean of y using, again, a single standard error term, but a single standard error term that integrates the variance from both our y and our x sample. Or, in our example that I showed you earlier, our level A and B. So the two variances are brought together. So with that in mind then, let's come back. I think I may have missed something on the back. No, we're good to go. With that in mind, where is our fifth condition when it comes to testing using a t? Well, it's embedded in the variance itself. Let's have a look at these two graphs again. First, let's look at the obvious thing that strikes us when we look at these two graphs. You can see that the mean between A and B, those two means differ. Right. Well, the same is true here. The means differ between A and B. All right, so that A and B differ, that's a common element between these two figures. Of course, the direction of that difference isn't the same, but that doesn't really matter, really. We can see that these two are different. Here, at least, A is less than B, and over there, A is greater than B. Sure, that's a difference between these two graphs, all right? But there is another difference, and let's have a look at that difference here. Up here, this table with the standard deviations, 7.6 and 8.6. Those two are pretty similar values. Over here, though, the standard deviation 12.2 and 4.3. Also different. The number of observations, 8 and 7 as opposed to 6 and 6. So there are two differences there that actually are important for us to take on board. And what those differences add up to is that the variance, the square of the standard deviation, the variance of factor level A and factor level B in this first panel, they're the same, or they're close enough to being the same for us to turn them as equal. Whereas over here in the second panel, this much larger spread here in A relative to B means that we can't make that same statement about the variances of A and B in the second panel. So the variance of A and B are not equal, or we can't assume them to be equal in this panel. And that is a big difference between these two. Yes, the direction of the differences is different, but the real important difference lies in the nature of the variance itself. That the variance is not equal on this side between factor level A and B, whereas it is equal between factor level A and B on this side. Now that really matters because an underlying implicit assumption of t-tests themselves is that the two levels we're comparing have equal variances. That is an implicit assumption. Sometimes it's stated explicitly, but it's implicit in all of our t-tests, unless we specifically state otherwise. And you will remember from ENVS 1003 that there are circumstances in which we do that. We do at times assume otherwise. So when we assume that there are equal variances, our confidence interval calculation stretches out a bit more. Remember before we had an X bar, we had a T, and we had a single term in here for our standard error term. It was the standard deviation divided by n. When we start comparing different levels within a single factor, of course we need to compare their difference, so x minus y, and then when we calculate our t, we need to include two sets of observations. We still have an alpha value in there, or our significance, and that remains the same, but we also then have two sets of variances. Now when we assume equal variance, strange thing about our two terms of variance here is that they're the same. Both of our terms here are for a pooled standard deviation, or a pooled variance here. And you can see they're divided by two different terms of n, so two different sets of observations. If those n's are the same as in our example, say 6 and 6, then we'll have two numbers here that are exactly the same. But what is the pooled standard deviation? Well, you can see that equation here, and you can see that the way that it comes about. The key thing is that it really is the same as a standard deviation calculation with a big difference, and that is of course that the numerator has two sets of squared deviances. Remember, the standard deviation calculation in the numerator has squared deviances. So you have these two sets of squared deviances being added together as a single numerator, being treated equally, hence the equal variance based calculation. So we have this underlying implicit assumption of equal variance, and it is embodied by that equation there. Now, if you're the type of person who doesn't remember equations and is freaked out by it, don't be, because I'm not going to ask you to remember that. All I need you to do, as I asked you in 1003, is remember that the equal variance test is called that because it explicitly includes an equal variance based element up here in the confidence interval, and it achieves that by treating the variances or the deviances from the two levels exactly the same in the standard deviation calculation. If we have non-equal variance, well, things change a little bit, and you can see that difference here. In the confidence interval calculation, the deviance for x and y are treated differently. So they are not treated as equal now. We have separate terms for them within our confidence interval calculation. The big change here, other than that, is that we calculate our degrees of freedom relative to the variance in the data set. Now, we're not going to dwell on that particular part of the calculation, but it's important to recognise that we overcome issues associated with the number of observations by scaling it relative to the variance. And that's what this calculation is doing. But the key element is up here, that we treat the variances separately because they are not equal. So the calculation itself explicitly handles that. Again, it's not essential that you can regurgitate or even memorize these equations. Just remember the difference between this equal variance based confidence interval and the non-equal variance based equation here, that difference is the difference between implicitly assuming, or rather explicitly representing, the variances as equal or treating them as different because they're not equal. Okay, so our big assumptions then, our 5 assumptions: continuous data, levels, 2 levels that we can split data between for a t-test. The data are normally distributed, tick, we saw that before. They are drawn randomly. That's a key element to our central limits theorem in the first place. And there are equal variances. We assume that the variances are equal unless we explicitly state otherwise. And that is where I stop for this introductory or refresher. If that moved a bit too quick and you feel like maybe a little bit more revision might be useful, have a look at those 2 Nature Methods papers. When you've done that, or before you do that, make sure that you complete the practice exercise that is online. Download JMP and install it on your machine. Use the free download from the JMP website. Then use the prac guide, the practice exercise guide, to run and interpret the tests. 2 different tests, one using equal variance, one using non-equal variance. And then have a look at the questions in that guide, because I'm going to ask you questions about the data and the analysis in our first stats session on the first day. Make sure that you at least have the analyses done, so that when we talk through the results, you at least have the results in front of you that you can refer to, and you can at least understand what the method is that we're talking about, that you have something to look at and interpret as we work through it. Ideally, you've already interpreted and understood the analyses by the time you get to the first day of ENVS 1002-6202 on our first day. I'll see you